Alright guys, so we're into the review for Unit 2, which deals with forces and energy. So again, just kind of reading through the topics here that you can see on the screen. The test is going to deal with forces, Newton's law of specific forces like gravity, tension, normal force, friction. The idea of centripetal force, Newton's universal law of gravitation, that's mostly the force ideas. And then we got into work, power, energy, different forms of energy, whether it's mechanical or non-mechanical, specific forms of energy like kinetic, gravitational potential energy, elastic potential energy, conservation of energy. So those are the topics on this exam or test. The way that I'm going to assess it, I'm going to have kind of a vocab section, which is matching. I'll have an action-reaction pair from a picture. I'll give you some examples, and you have to decide which of Newton's laws is best being demonstrated in that example. We're going to talk about the factors and proportionality of either the centripetal force or universal gravity, work and power problems, so similar to what we do in the staircase lab. Force problem chart, so just a basic force problem where you have the chart and you're going to fill out all the information, draw a free body diagram, figure out the different specific forces using the chart, using the equation, solving for things. And then finally, conservation of energy with numbers and with kind of explaining what's happening to the different forms of energy as the situation changes. So in the review, we go through very similar type problems to what will be on the test. So the first part of the review is basically the terminology. So I'm going to skip over this because you guys have access to Google or the internet or the videos that I've provided already. So I don't need to go through every one of these definitions or ideas, because hopefully you've learned them and you can kind of talk about them intelligently. The test doesn't ask you to write out definitions anyway, but you should remember the ideas and concepts and be able to apply them. Units are always important, so make sure you're familiar with units. All right, so the first problem here on the review, or question on the review that is not just like a strict vocab definition idea, is a picture, and in that picture there's an action-reaction pair. So you have to just identify one action-reaction pair. It's up to you. There's usually several within one picture, but there's an obvious one in this. So remember, for an action-reaction pair, that deals with Newton's third law of motion. Sorry, I'm trying to get something to move here. There we go. So for Newton's third law of motion, the concept, that's not what I want. Sorry, there we go, that'll work. So the third law, which is dealing with action-reaction pairs, is the idea for every action there's a equal and opposite reaction. I talk about it as kind of caveman talk, so you just write out a basic statement that describes the two nouns that are involved, or two objects that are involved that are pushing or pulling, and then direction. So I have done this in previous videos, but for this one, the two objects that I have here, I would have the ball and the foot. All right, and they are interacting, they're pushing on each other. So the thing that I would probably start with is the foot. So I would say the foot. And we just need a push or a pull. So you just pick one of those two verbs. So I would say the foot pushes the ball. So the two objects, the foot and the ball, and the direction that the foot is pushing on the ball, I would describe here in this picture as up. Okay, so the foot is pushing on the ball going in the upward direction. And then that what I would call the action. For the reaction, all you do is switch and flip. So you're going to switch the order of the two nouns. So in the nouns, it would be the ball and then the foot, and the ball pushes on the foot still, because the noun is still the same noun, so it's still push. So the ball pushed the foot, and it goes the opposite direction, so that would be down. So the switching part is just you switch the order of the two nouns, and the flipping is the direction, or the arrow flips in the opposite way. These two forces, though, they are equal and they are in opposite directions and they are balanced. So that's the first one, where you're identifying an action-reaction pair. You're going to have to do similar things. It'll be a different picture, but it's the same kind of idea. You look at the two objects interacting, that's essentially touching, and then you describe the force that one is exerting on the other, and then you do the switch and flip technique and get the other one. Okay? So that's action-reaction pair. For the next part, you're going to identify which of Newton's 3 laws of motion is being exemplified. So again, exemplified as being demonstrated. In actuality, all 3 laws are happening at all times, but these are written in a way supposed to kind of generate one type of law that you want to think of. So again, just kind of revisiting those. So the first law is the law of inertia. And inertia is the tendency of a body to do what it wants, like what it's doing, to keep doing what it's doing. So this is one where it's like you have 2 types of object behaviors. So we have an object can be at rest. It can also be in motion with a constant velocity. And it wants to stay at rest. And the object in motion wants to continue with a constant velocity. And the only way it changes, so that's the tendency of a body. That's the inertia idea. So the inertia keeps something from moving, or keeps it moving at the same speed. But if it's not doing those, it's because the net force is, it changes because the net force is not equal to 0. So if you have a net force that is not equal to 0, then your object is going to be, that means that your object accelerates. So the force causes the acceleration, and that acceleration occurs, and the object is no longer at rest, or it's no longer moving with a constant velocity. So it can increase velocity, decrease velocity. It can also turn, which is a change in velocity as well. So accelerations cause changes in velocity. It's the rate of change of velocity. Okay, so coming back to these examples, I'm gonna underline the things that I think are important and helping you identify what law is which for each of these examples. So it says to cause the same acceleration for an, oh, sorry, I skipped ahead. That was the first law. Second law is the simple one, which describes the acceleration is proportional to the force, the net force, and inversely proportional to the mass. So another way to write this is F net equals ma. But I like this one better because it actually is really what's happening. So you can change their force, you can change your mass, and based on those types of things, you get a change in your acceleration. So to get the same acceleration for an empty and a full shopping cart, so we have a full shopping cart and an empty shopping cart, you have to push this should say full shopping cart with more force. So the more you push, or if the mass increases, you have to increase the force to keep the same. And if the mass is less, you don't have to push as much, so the force is smaller, and you get the same acceleration. So again, obviously, this is all dealing with F equals ma, so this is the second law. All right. The third law we just went over in the previous example, so that's the action-reaction pair. So that's dealing with equal and opposite forces. So this one, I think I look for directions like left, right, up, down. Those kind of ideas, forward, backward, those are going to help you identify it's the third law. So no, the first one is the second law. The second example says the computer does not move by itself. So that's an object at rest is going to stay at rest, and that's because the net force is 0. So that would be the first law for that one. And then the third law is the third example, where it says while swimming, you use your arms to push the water backward, and the water propels you forward. So your arms push backward, and the person moves forward, so that is that opposite direction, and it's equal forces in opposite directions. So so that is those things. With these examples, don't add more things. So just read what is there and make your decision based on what's there. Again, it should be very obvious as to which one it's trying to demonstrate. Okay, so this is kind of the idea with proportionality, or kind of how different changes in the variables will affect the different forces. So Newton's universal law of gravity, we've talked about that. That's big G m1 m2 over r squared. And it says explain how changing the mass or separation between the masses would affect the force of gravity between the objects. So we did a simulation lab to help with this, but if we kind of look at mass as the factor, and again, the equation tells you how it's set up, we're going to see how this force changes if there's a change in mass. And it doesn't matter if it's mass 1 or mass 2 or both of them, but we just want kind of the net change. So let's say we make this mass get bigger. All right, so I'm going to put this over 1 so we can see proportionality. The mass is in the same part of the fraction. It's in the upper part of the fraction with these masses as the force of gravity. So if it increases, there increases. So if mass increases, there's an increase in the force. So if you have more massive objects, there's a bigger force of gravity. So if we're thinking about a situation with like the person in the earth, a heavier person or more massive person is heavier because their mass is getting bigger and their weight, which is the force of gravity, would get bigger. The exact opposite is true as well. So if the mass gets smaller, then the force of gravity would get smaller. It's a direct relationship, so they do the same thing. With the separation, that's the variable r in the formula. So if you think about this, if I make, and this is r squared, but I just want to change r, so I'm going to make r get bigger. If r gets bigger, I'm dividing the numerator by a bigger number in the denominator. So if I divide by a bigger number, it's going to make the force get smaller. So they are indirectly related because they're in opposite parts of the fraction. So same parts of the fraction, direct relationship. So if the separation increases, the force of gravity gets weaker, and that's an indirect. In this one, it's an inverse square law because of it's squared, but you don't have to really worry about that. You just have to talk about how would changing the mass affect the force of gravity, or how changing the separation would change the force of gravity. And again, this makes sense, right? Because like if you're close to the Earth, you weigh the most you are going to, but if somehow I moved you very, very far away from the Earth, you're going to feel less gravity there, so the force of gravity goes down. The force of gravity here is big. Okay, so that's the idea for that situation. Okay, so we're finally getting into some problems here, and we'll go through those concepts. So in problem number 1, it reads a person is going to push a shopping cart, and the shopping cart has a mass of 15 kilograms, horizontally, so to the right, down the aisle with a force of 120 newtons. I'm assuming it's right. This is a positive number, so that's why I would think it's to the right. So this is the pushing force, so that's there. If the coefficient of kinetic friction is 0.35, so that's going to be U, and you could write UK, but U is good enough. That's the coefficient of friction. We're going to determine the acceleration of the lawnmower, so that's the ultimate goal, is to figure out the acceleration. So I'm just starting with a dot to represent the shopping cart, and we're gonna draw the forces that are acting. So if you think about the shopping cart, the force of gravity is definitely going to try to pull down on the shopping cart. So I have an arrow, force gravity going down. There is the floor that's holding it up. That's the normal force. If we think about the up and down, those should be balanced because the shopping cart doesn't typically fall through the floor of the supermarket, nor does it get thrown upward into the air by the floor. So these are just balancing out. To the right, we've described a pushing force. And to the left, there's going to be a force opposing it, and that's going to be the friction force, and I have that going to the left. You could write FFK, or you just write FF, that's fine. So again, X directions are left and right, zeros in the middle, right's positive, left's negative. Y components, zeros in the middle, up's positive, down is negative. So for these forces, I'm just going to label them out. So I have my pushing force, my gravity force, normal force, friction. If you want to write kinetic, you can. When you add those up, you get the net force. Again, the next step in this process is doing the positives and negatives and zeros. So the push is going to the right, so that's going to be positive in the X and 0 in the Y. Gravity is going down, so that's 0 in the X and negative in the Y. Again, just match up with the component. normal force is going up, so that's 0 in the x because it doesn't go left or right, and it's positive in the y because it's pointing upward. And then finally, friction in our forces or our picture is going to the left, and it doesn't point up or down, so that one's 0. We already said these two forces are balanced, so when we add the y component, when we put all these together, we get 0. So we need to plug in numbers that we can. So our pushing force was labeled at 120 newtons. We don't know anything else, so we're going to have to do some math here and solve. So the force of gravity is the first thing we're going to work with. So force of gravity is just mg. So the mass is 15 and gravity is 9.8. So if you multiply 15 by 9.8 in your calculator, you'll get 147 newtons for the value. I'm going to put that in this box. That leads us to our column, our y column, with just one empty box. So if I have 147 newtons going downward here, I need 147 newtons going upward to balance it out to get to 0. Right? So our normal force is a positive 147 newtons. If you wanted to put negative here, that's just the direction it's going down. The positive means it's directed up. Okay. So we figured out our normal force, which is going to be able to lead us to figure out our force of friction. So the force of friction is, the equation for it is fun. So the kinetic friction, kinetic coefficient. So our coefficient of kinetic friction is 0.35. And our normal force is 147. We multiply those together. 0.35 times 147 is 51.45 newtons. So I'm going to put that in this box. It's negative because it's pointing to the left. So that's a negative 51.45. And then if we had our pushing contest or our tug of war, we have 120 going to the right. And we have negative 51.45 going to the left. So if I add those together, I get the net force, which is something like 68.55 newtons. We're not quite done, and it's positive. That makes sense, so it goes to the right. We're not quite done. We have to solve for the acceleration. So to get that, you can use the net force is equal to the mass times the acceleration. So 68.55, it's positive, equals the mass, which we said was 15, and we're going to look for A. So you divide by 15 on both sides, and you get an acceleration of 4.57 meters per second squared. It's going to the right because it's a positive and it's in the x direction. All right, so a similar problem you'll encounter on the test where you have some forces acting. It might not have, it doesn't have the same numbers obviously, but it might have a constant velocity, or it might stay at rest, or it might be slightly different, but the concepts are still the same kind of equations using the chart, positives, negatives, zeros, getting a good getting a good free body diagram, and then being able to solve for acceleration or work with this Newton's second law is necessary. All right. Going on to the next problem, it says there is a 24 kilogram child, so that's the mass, that's starting at descends a 5 meter high slide. So this is actually a really big slide. It's starting there, so I'm going to say height initial for HI. It reaches the speed or the ground at a speed of 2.8 meters per second. So that's a velocity, and it's the velocity at the end. So if I was just drawing a picture, there's the slide. Here's the kid. And they're going to start up here at this point, which is the initial point, and they're going to end down here moving at the final point. Everybody okay with those kind of initial and final values? Hopefully you are. So it tells you the height initial, and then this is the velocity final. So we're going to kind of calculate different things. The thing I like to do with these, again, is do the LOL graphs. So in the LOL, the child, the earth, and the slide are going to be in our system, and we just have to identify what kind of energy it has at the top. So at the top here, it doesn't say the child's moving, it just says it's at a height. So I'm going to ask you on the video, what type of energy is this? And hopefully you answered that this is gravitational potential energy, or GPE. So I don't know the numbers that make this up. We're going to figure that out later, but that's just GPE. That's the only energy I really have. The kinetic energy would be 0 because it's not moving. We haven't created any heat or sound, so that's also 0, or transformed any of these energies into heat or sound or non-mechanical energy. So the total energy that I start out with this total energy initial, and this is the initial point, it's just equal to the gravitational potential energy. So the gravitational potential energy in the beginning is equal to the total energy in the beginning. We're going to do a same type of chart here, except we're going to do the final position. So the final position, GPE final, KE final, NME, and then I ran out of space, but total energy, TE, that's going to go up here in this. And these are all at the final position. All right, so at the bottom, it has kinetic energy. I don't know the amount. It also asks in part C, if you read, it says determine how the, or sorry, determine, oh, I left it off. So it says determine how the system's energy changed from the top to the bottom. So we're going to compare those, but I'll do this calculation and we'll figure out NME here. So I'm going to do that math later on. So we're gonna have NME and we're going to have KE. There isn't any gravitational because they're at the ground level. So that's 0 for height final. Just like velocity initial was 0 here because they weren't moving. Okay, so let's go ahead and do this math. So to find the gravitational potential energy at the top, or initial, it's going to be mgh initial. So m is 24, g is 9.8, and then the height is 5. So if we multiply those three numbers together, you get 1,176, and it's going to be joules because that's what energy is measured in. If we want to figure out the kinetic energy at the bottom, it's 1/2 mv squared. So 1/2, the mass is 24. The velocity is only 2.8. Make sure you square just the velocity. When you do that, 2.8 squared times 24 times 1/2, you'll get something like 94.08 joules. So far, so good. So you can see that the total amount of energy for gravitational, that's supposed to be 1176. And then this kinetic energy bar is a really small number. It's only like 94-ish. So there's non-mechanical energy here. So these non-mechanical energy, which we don't know what that is, but I'm going to do that here and figure it out. That's what we're going to solve for in this. I'll call this B part 2. I left it off the sheet, but that's the concept. So so these two added together, this kinetic energy plus the heat energy, that's the total at the end. So the total in the beginning, total at the end. And the total at the end and the total in the beginning, they should be equal because conservation of energy says the total energy initial equals the total energy final. So this one, again, is a little bit more like the skate park when you had friction involved and you saw the energy bar for non-mechanical energy continue to increase as the person went back and forth across the ramp. So in the beginning, it's all GPE. At the end, it's kinetic energy and non-mechanical energy. Finals here. This is initial. So 1176 equals 94.08. And then we're looking for the non-mechanical energy. That's this part here. So to do that, you just subtract 94.08 from both sides. And the non-mechanical energy is something like 1081.92 joules. So that is how much energy was transformed from mechanical energy into non-mechanical energy. Remember, the mechanical energy, ME, those are the energies that can do work, and that's the GPE and the KE. If you also have spring potential energy, that would be a form of mechanical energy. So this was part B2 or whatever here. So so again, the concepts is really what we're looking at, and that's what we're going to answer down here. So we're going to look and see how the energy in the system changed. So to figure out the change, you compare the change in energy would be comparing the final energy and taking away the initial energy. So like, did it get bigger? Did it get smaller? Just kind of conceptually looking at it and then giving a reason why. Like why did the energy increase, decrease, or stay the same? I'm going to erase this because I wrote in the space that I need to answer the last questions on this problem. Cancel that. No. Undo. There we go. All right. So so what we need to do is talk about GPE. So GPE is based on height. If we look at the energy bar, we had in the beginning, GPE initial was 1176. GPE final, and again, you don't have to do this with numbers, but I think it helps, is nothing. So how did it change? The gravitational potential energy, there was a change in it went down, it decreased. GPE got smaller. And the reason why it got smaller physically is because the height got smaller, right? So we started out at a height of 5 meters, and we went to a height of 1, and again, the equation for GPE is mgh. The mass of the person didn't stay the same, that was constant, gravity was constant. This h is what changes in this problem, and height got less, therefore the gravitational potential energy got less. Thinking about kinetic energy, the kinetic energy initial was nothing because it wasn't moving. The kinetic energy at the end was 94.08. That's what we got. So to go from 0 to 94.8, there'd be an increase in kinetic energy. If you want to think about it this way, what causes the kinetic energy to change? Ke is equal to 1/2 mv squared. Again, we said half is a constant. It doesn't change. Mass is also a constant in this problem. The kid didn't gain or lose any mass. The velocity, though, increased. So if there's an increase in velocity, that's a direct relationship with kinetic energy. So as velocity increases, so does the kinetic energy. Mechanical energy, that's the kinetic plus potential put together. So in the beginning, it was 1176, right? That was our gravitational potential energy was 1176. Our kinetic was 0. At the end, it's kinetic and potential GPE final. I left out a G here, sorry. So at the end, there is no gravitational potential energy because the height's 0, and the kinetic energy is only 94-ish. So it went from 1176 to 94. So the mechanical energy dropped. It went down because, basically 1176, the initial is larger than the final, which is 94 or so. Okay. For non-mechanical energy, we didn't have any in the beginning. And at the end, we calculated and we had the value that I erased, which was something like 1,000 at the end, 1,082-ish joules. So the non-mechanical energy increased because mechanical energy changed into non-mechanical energy. Heat and sound increased. There was friction essentially in this problem. The last part is total energy, and total energy, the answer is as long as it is a closed system, which this was a closed system, the total energy initial and the total energy final are equal because there was no work from external forces. So there was no outside force making this person go faster or slower. We included the friction in the slide as part of our system, so that's why we talked about it as non-mechanical energy instead of work. All right, so one more problem to go. I'm trying to beat the 30-minute mark. So it gives you a situation where two motors, motor A and motor B, can lift a block of different masses to a height, different heights in different amounts of time. So I'm going to draw A. A is supposed to be 10 kilograms, so that's the mass of A. The height that A goes to is going to be 4 meters, and the time for A is 20 seconds. For B is 15 kilograms, so I'm going to make it slightly bigger. So that's the mass of B. The height of B is also higher, so that's 5 meters. It got cut off, or it's over on this side. And then the time that it takes for B is 40 seconds. So we have all those ideas. Essentially, we're lifting things up, so we're going to apply a force up on both of these, and they're going to both move up, right? So distance A, distance B, force B, force A. All right, so again, this is similar to the lab that we did where we're thinking about going up and down steps. If you didn't do that lab, then in order to lift something, the idea is you have to lift with a force that is at least the minimum equal and opposite to the force of gravity. So the applied force, or the push or the pull, the force going up has to balance that out in order to get it to move. So once you get it moving at a constant velocity going up, all I have to do is counteract this gravity. So the force of A is really the force of gravity of A, and the force of B is really the force of gravity of B. So those are the forces that need to be applied. And we've already established in this unit that the force of gravity is just m times g. So we're going to use that. The distance that we're lifting it, that's going to be the height. So this first distance of A is 4 meters. B goes up further, so B goes up 5 meters. All right, and I think showing work is the easiest way to go about this. So we're going to use the equation for work, which is FD cosine of theta. The cosine theta, that's the angle that is between the force and the displacement. So if we think about our force vector is directed upward in both of these instances or cases, and the direction that it moves is also upward. So if they point the same way, which is what we have in our situation here, theta is equal to 0 degrees, and they agree, so cosine of 0 just gives you 1. So that's the maximum value that you could get. So for part A, for the work for A, it's going to be the force times the distance times the cosine of the angle. It's going to be the A ideas, so this is like the mass of A times the gravity of A, which is the same gravity that we had before. It's just 9.8 because it says it's Earth, or it doesn't specify that it's not Earth. And then the distance of A, there we go, distance of A, and then cosine of theta is just going to be 1 for both of these. So so this would be 10 times 9.8 times 4. So if we multiply that out, we'll get 392 joules. So that's the work for A. The work for B, similarly, is going to be the force of B times the distance of B, the cosine of the angle that the distance or displacement and the force do. Again, that's going to be 1 because they're both pointing the same direction. So it's mb d, or md times g times the distance that B travels. So that would be the 15 times 9.8 times 5. And if you put those together, you get something like 735 joules. So 735 is bigger than 392. So the work by B is bigger than the work for A, and you can just refer to C math. Okay. So the idea though is in B there's a bigger force and bigger distance. That's going to equate to a bigger work. So both those factors influence that. The last part here, so I'm going to draw a little line to divide that up so we have a space. We're trying to figure out power. So power, the equation for power is work divided by time. So really you just have to take those answers that we got for each one and divide it by the individual time it takes for them to move those displacements. So the power for A is the work of A divided by the time for A. So the work of A was the 392 value that we got, and we're going to divide that by the time that it takes for A, which is 20 seconds. So if we do 392 divided by 20, that's 19.6. It's going to be watts for power. So 19.6, that's the power of A. For the power of B, we're going to take the work, which is 735, and the time is 40 seconds this time. So I skipped a step. Let me write that out. So power B, work B over time B. Okay, so if you put that in your calculator, you're going to get a value of 18.375 watts. So again, comparing them, the power of B is greater than the power of A because it does work more quickly. That's essentially the thing. So it takes about twice the time to only go 1 meter more. So it's doing the work faster, which makes it more powerful. So those are your two answers to problem number 3 here that deals with work and power. A little bit over the 30-second threshold, but not too bad. So hopefully this is a good review for you guys. If you have questions, again, reach out and I will try to clarify. Have a good one.